Welcome back to the Explainer. Okay, I am seriously thrilled you're here today because we are going on an absolute journey. We're going to completely demystify the physical, tangible infrastructure that actually powers all those trillion parameter AI models we keep hearing about. We're doing this by literally zooming out. We're going to start all the way down at microscopic silicon and scale up, I mean way up, to the massive warehouse-scale AI data centers of tomorrow. Specifically, we're looking at NVIDIA's NVL72. Let's get right into it. Here's the roadmap for our zoom out. We're going to hit the CPU GPU superchip, Blackwell, the AI engine, scaling up to the NVL72, powering the AI factory, and finally, the hardware roadmap.
All right, part one, the CPU GPU superchip.
So to really wrap our heads around AI at a massive scale, we actually have to start incredibly small. What's absolutely fascinating here is this concept of the illusion of one. When we talk about a Blackwell GPU, we aren't actually looking at a single monolithic chip. Why? Well, physics. Manufacturing limits literally prevent us from making a single silicon die that large. So instead, you're looking at two separate reticle-sized dies, but they're unified by a blindingly fast 10 terabytes per second interface. 10 terabytes! Because they communicate so perfectly over that link, the software just sees them as one single unified GPU. It's wild.
This specific approach is called a multi-chip module, or MCM. By splitting the design up, NVIDIA completely bypasses a massive physical manufacturing bottleneck. It lets them cram an astonishing 208 billion transistors into just this single module. And crucially, it lets them pack 192 gigabytes of lightning-fast HBM3E, that's high bandwidth memory, right next to those computing cores. That physical proximity is exactly what keeps these chips fed with data at insane speeds. You gotta keep the beast fed, right?
Okay, let's zoom out one step further. Enter the Grace Blackwell Superchip, otherwise known as the GB200. You've got an ARM-based Grace CPU sitting right there in the center, and it's flanked by two of those dual-die Blackwell GPUs we just looked at. They are all packaged together on a single board, functioning as one incredibly potent computing engine. Now, the real so what here is how this exact layout completely shatters the notorious memory wall that plagues older hardware. In a traditional setup, CPUs and GPUs have separate memory pools. They awkwardly shuffle data back and forth over a slower PCIe motherboard connection, maybe doing, 64 to 128 gigabytes per second? But with this superchip, the CPU and GPUs share a massive, cache-coherent, unified memory pool. They're talking via a custom link called NVLink C2C at about 900 gigabytes per second. That'll bottleneck? Totally gone. Moving on to part two, Blackwell, the AI engine. Having seen the physical layout, we need to look at the actual brute force computing engine inside these things, and it really comes down to how they do the math. Modern AI, especially when it's generating text or images, doesn't always need perfect, hyper-detailed decimal precision to get the right answer. By intentionally shifting to lower precision numerical formats like FP4, which is a 4-bit floating point, the hardware can calculate way faster. Plus, it literally takes up half the memory of the previous 8-bit standard. That means you can fit much larger models directly onto the chip itself. And the throughput jump here is just massive. By utilizing this FP4 precision, the Transformer engine delivers a 4 times leap over the older FP16 standard. This right here is the secret sauce for real-time inference. It's the exact reason an AI chatbot can spit out responses faster than you can even read them, even when running massive models that would have completely choked older hardware. Just to ground this in some reality, when you take these FP4 capabilities and put them together in a full rack, the system hits 1.4 exaflops of compute power. An exaflop is a billion operations per second. Yeah, a billion. We are quite literally talking about taking the power of the world's fastest supercomputers and cramming it into a single standardized server rack. Part 3. Scaling up, the NVL72. So, we've seen the raw, unadulterated power of the individual engine. Let's zoom out again and see how we actually build the factory. What we have here is a single 1U compute tray. It slides right into a standard server rack, and it contains 2 of those Grace Blackwell superchips. So in just this one flat tray, you've got 4 Blackwell GPUs and 2 Grace CPUs, all working in perfect harmony. But, a single tray isn't a factory. The true magic happens when you start connecting these trays together. NVIDIA uses an architecture called the NVLink switch fabric, which connects every single GPU in the rack so they can talk to each other in a single hop. We are talking about a staggering 130 terabytes per second of bandwidth across the network. Plus, it features something called Sharp, that's in-network computing. Basically, the network switches themselves actually help calculate data as it passes through, which dramatically reduces the workload on the GPUs. Talk about efficiency, right?
Let's see how this all builds into our ultimate zoom out, the NVL72 rack itself. This is a fully integrated, pre-built appliance. It stacks 18 of those compute trays together, alongside the networking switches, to create a system where 72 GPUs and 36 CPUs act flawlessly as one single gigantic machine. You literally just drop it into your data center, plug it in, and boom, you have an AI supercomputer ready to go. Part 4. Powering the AI factory.
Of course, bending the laws of physics to create this kind of compute density brings some immense real-world infrastructure challenges. I mean, you can't exactly just plug this thing into a wall outlet. A single, fully loaded NVL72 rack pulls up to 130 kilowatts of power under a maximum load. To put that in perspective, older racks used to pull maybe 10 to 20 kilowatts. With this, you basically have a mini power substation sitting right there on your data center floor. It requires highly specialized power distribution just to ensure that when all 72 GPUs surge to calculate a prompt at the exact same millisecond, they don't, accidentally trip the entire facility's power grid. And where there is massive power, there is massive heat. You physically cannot cool 130 kilowatts with air alone. It would require fans blowing at hurricane forces, which is just completely inefficient and deafening. So this level of density strictly requires dedicated liquid cooling. The rack has internal loops, pumping 150 to 200 liters of water per minute directly over cold plates attached to the chips. This keeps the silicon happily sitting at a nice 50 to 70 degrees Celsius, meaning the chips never have to slow down or throttle because they're getting too hot. But there is a physical consequence to all this density. When you add up the silicon, the thick copper wiring, the networking gear, and the literal liquid coolant running through the pipes, this single rack weighs in at about 3,000 pounds. That is the weight of a small car, completely concentrated into just a few square feet of raised data center floor. Data centers actually have to structurally reinforce their concrete just to hold these machines up. Absolutely wild. And finally, Part 5, the hardware roadmap. If you think 72 GPUs acting as one 3,000-pound machine is wild, hold on to your hats. NVIDIA's roadmap shows they're just getting started with this scaling process. They're aggressively trying to double capacity every single year. We just explored the Blackwell generation, but look at what's coming. In 2026, we see the Vera Rubin architecture, moving to a 3-nanometer process, a faster NVLink 6, and potentially quad-die modules that could push 4 exaflops per rack. And then, by 2028, the Fenmine generation aims to shrink down to 2 nanometers, specifically optimizing for the massive inference demands of reasoning AI models. The pace of this innovation is just relentless. And that brings us to the most exciting question of all. We've seen how we scale from a microscopic transistor all the way up to a liquid-cooled 3,000-pound mega rack. As these hardware boundaries double year over year, pushing into multiple exaflops, what previously impossible AI models is this going to unlock next? How will this relentless micro to macro scaling fundamentally change the software and reasoning capabilities of tomorrow? It is a fascinating space, and I highly encourage you to keep your eyes on it. Thank you so much for learning with me today, and I'll catch you on the next explainer.